Hello everyone, my name is Haozhe Zhang, and I'm here to present our work, F-IVM, Learning over Fast Involving Relational Data. This is a joint work with
Milos Nikolic,
Ahmet Kara,
and Olteanu.
Let's first describe the setting for our work. The training dataset for our machine learning tasks is defined by a feature extraction query that is executed over a relational database. An example of such a query could be the nature join of all relations in the database. This training dataset is then used to construct machine learning models. But the database changes and updates, so our goal is to keep these models up to date. However, computing and maintaining the training dataset can be very expensive, especially when updates are frequent. To tackle this problem, F-IVM does not materialize the training dataset, but instead rewrites the learning task into a set of aggregate queries. F-IVM further decomposes these aggregate queries into similar queries, and then create efficient maintenance strategies for them. The unique feature of F-IVM is that many diverse learning tasks can be supported in a uniform way by generalizing them into aggregate queries over application-specific ring values. One example of such values are multi-dimensional tensors. More details about techniques behind F-IVM can be found in our paper from SIGMOD 2018. We will demonstrate F-IVM for three machine learning applications: model selection, ridge linear regression, and Chou-Liu trees. Model selection is the task of selecting the features that are most relevant to a given label. The relevance or the degree of correlation between one feature and the label is captured using mutual information. F-IVM computes the mutual information between all features and the label, and this task can be captured using a set of group-by sum aggregates. Ridge linear regression learns the parameters of a linear function that fits the data best. The parameters of this function can be learned using batch gradient descent. In order to speed up the gradient computation, F-IVM computes the covariance matrix that captures the covariance between any pair of pictures. The third application in this demo will construct the Chou-Liu tree, which is an efficient way to model the joint probability distribution of the underlying dataset. In order to construct a Chou-Liu tree, F-IVM computes the mutual information for all pairs of attributes in the training dataset. We will demonstrate these three applications using our web-based interface. In the input type, we can select the training dataset, real-world dataset from an industry collaborator. It is used by a retailer for business decision support and forecasting user demands. The query is defined by the nature join of the five relations. The blue variables are the join variable, and we simulate the streaming dataset by interleaving insertions to the input relations in a round-robin fashion. This tab demonstrates the model selection phase. We can specify a label and a mutual information threshold. The left column then shows the pairwise mutual information between the variables and the label. Only the variables above the threshold bar are selected as the features. By clicking the play button, new tuples are inserted into the dataset, and F-IVM updates the mutual information for each block of updates. This number shows the progress of the updating. We can observe how the mutual information values change. Here we set the label to inventory units, and we select these variables as the features. The regression tab allows us to inspect the linear regression model with the features and the label chosen in the previous tab. This covariance matrix represents the pairwise covariance between the features, which are captured by a collection of aggregates. For example, this cell is the covariance between inventory units and price. Since these two variables are continuous, the covariance is a scalar, which is the aggregate sum inventory units times price. For categorical variables, we need group bys. For example, for this cell, the covariance between two categorical variables, subcategory and category cluster, it is a 2D tensor, which represents the aggregate sum1 grouped by subcategory and category cluster. In other words, A cell in this tensor represents the occurrence of the corresponding values in the joint result. An empty cell means the corresponding values do not appear in the joint result. Although we show the tensor as a 2D matrix, F-IVM stores these values with a sparse data structure for saving space. In total, F-IVM has to maintain more than 1,500 aggregates. Now with the updated covariance matrix, we can use a batch gradient descent solver to update the model parameters. The parameters are scalars for continuous variables and vectors for categorical variables with one parameter per value. We can try this model now. Here, we can take a tuple from the test dataset. These categorical values are transformed to one-hot encoding. Then we do the dot product of the two vectors to get the predict result. The parameters are trained based on the current inserted tuples, which is about 1% of the whole dataset. This tab shows the mutual information matrix for all pairs of variables in the dataset. The mutual information values used in the model selection tab is just one column of the matrix for the selected label. When we launch the streaming, we can see the change of the values in the matrix. The degree of the red color indicates the values of the mutual information. Darker red means higher correlation, while lighter red means more independence. We compute the mutual information of any two variables using a set of aggregates. For this matrix, F-IVM has to maintain more than 1,600 sum group by aggregates. A lot of them are already computed when maintaining the covariance matrix. We can share the computation across applications. Trivial trees can be built by building maximum spanning trees, where vertices are the variables and the weights of the edges are the mutual information between them. We compute the trivial tree based on the updated mutual information matrix. These two boxes show the trivial trees before and after the new bulk of updates. We can see there are mainly two clusters of variables in this tree, with one centered as cell area squared feet, another one centered as average height. These two variables are the center because they have relative higher mutual information values with others. This new tree differs from the old tree. For example, for this variable, Pacific, it's now between the two clusters. This meant because this variable now has higher mutual information values because of the update. The strategy tab displays the maintenance strategy for the input query. F-IVM constructs a tree of views with the 5 input relations as leaves, the query result as the root, and each view defined by the join of its children, with possibly variables aggregated away. For example, this leaf view is the input relation inventory. Its parent view is constructed by aggregating away the non-join variables. The above views are defined as a join of their children. So the final query result, the join of the input relations, is then stored in the root view. Assume there is an update to atom. We can see how the red update tuple is propagated bottom up. F-IVM computes the data views along the path and applies the data views to the original views. In our example, F-IVM first computes this data view by aggregating away the variables except KSN. And then to compute this data view, F-IVM finds all the location and the data ID values paired with this KSN. And then in the views above, it filtered out the values that are not in the joined views. Our backend engine dbToaster builds hash indexes on each view over the join variables to make sure we can do these operations efficiently. F-IVM takes a query and the variable order of the query as input, generates the maintenance strategy using an intermediate language named M3, and then compiles the M3 code to optimize C++ code using dbToaster. One unique feature of F-IVM is that the maintenance strategies we just discussed apply to all aggregates over this query. Each tuple in these views maps to an array of aggregates that will eventually contribute to the aggregates in the root views, which are the aggregates required by the two matrices. So F-IVM maintains only one instance of this view tree and use rings which define the sum and product operations of the aggregates to capture all these applications. For more complex applications, we just need to define richer rings or even composition of rings. By taking advantage of the uniform strategy and the shared computation across the applications, F-IVM updates the batch of aggregates for both the covariance and mutual information matrices about 2 orders of magnitude faster than if it would update them individually one after the other. This is the content of the demo. Thank you for watching.